Okay. Four more installments of this course. You'll probably see me 5 more times because there's a final exam, right? Don't forget, we have a final exam. I think it's on May 3rd from 1 to 3. The university sets those timings. I'll send an announcement, etc. The muddy points are nonlinear solvers. Thank you for answering that. So I'll start working on addressing those questions. Final exam will be in the same spirit as exam 2, etc. And your homework, this week's homework due is the last homework you will have. So we're not gonna do. Thank you for you are gonna get the award for the most enthusiastic student. Actually, let's do this year. I think I did it one year. We gave some awards to students, like the most participating, the most chatty person, the most enthusiastic. Maybe we'll do it this year. So we will not do a homework on boundary value problems. Unfortunately, there's just not enough time. However, I will explain this to you in class. We'll do the coding together, but you are responsible for understanding it very clearly and very well. And do leverage the student hours that I have this week and next week and before the exam as well. I'll still hold the session before the exam. And yeah, we are on the last section of this course. I can't believe it kind of went by so fast yet. You're like, okay, we want to be done with the semester. We're almost there. Okay, now the other phase of ordinary differential equations, if you remember when we classified them, we had initial value problems, things where you have an initial condition that evolves subject to the governing equation. The right-hand side, d phi by dt is some right-hand side. And typically those are also associated with time-dependent problems. So whenever you see time and a first derivative in the ODE, one initial condition, you're most likely dealing with an initial value problem. The other side of ODE problems is boundary value problems. So in those problems, you are typically given conditions along the boundary of where your problem exists. So for example, I want to understand the air moving in this room, right? So I have a boundary over there. That's the door open. There's some air coming in. I have the inlet vents of the AC. I have some return vents as well. And maybe I have this door open. So you specify only the boundary conditions. Those are the information that you know. And then you see what happens inside your domain. So this would be our domain. That's kind of the description that I'm showing here. Because it might not be clear, like, what is a domain? Go back to the problem we did when we did the heat transfer inside the rod, okay? Remember that? So that was fixed, had fixed temperatures on the edges. Those are the boundaries. And then we studied the evolution of the temperature inside the rod. This is the most classic problem in boundary value problems. So we'll only look at second order ODEs in this case. So they might have a first derivative in them, or they might not, but that's okay. But given that they're second order, they need two conditions, one at each boundary. So if you look at this rod, in this case, there's this rod held at fixed temperatures on each side. Clearly, based on the value of those temperatures, it might be heating or cooling the rod. But we're also, one of the problems we dealt with was called the convection heat transfer problem. You'll study that later in your engineering courses. But suppose you're blowing air at some temperature on this rod, and that air temperature is going to interact with the heating that is occurring from the boundaries or cooling from the boundaries, and it's going to produce a temperature distribution. We solved this problem in chapter 1, chapter on linear solvers, chapter 3, I guess, or chapter 2. Okay, now we're going to understand. Remember when I kept talking about the system of equations and the Thomas algorithm, and I told you at the end of the semester you will learn how we obtained that system of equations. Today you will learn that. In the next few lectures you will learn how we obtain that system of equations. Okay, so the governing equation in this case is this second order ODE. You know it's an ODE because you got one independent variable, which is X, the location along the rod. T is the temperature, every point inside the rod. And whatever is on the right is a bunch of coefficients here, have to do with the properties of the rod. But you have on the right-hand side, you have the temperature itself that you're solving for, and T infinity, which is the temperature of the air that's blowing on the rod. So depending on T infinity, you might be cooling the rod or heating the rod, okay? And these are the properties for, HP over lambda AC. We're gonna call all of this capital H in the next slide. So don't worry about that. What matters now is that you have this equation and you have two conditions, a fixed temperature on the left and a fixed temperature on the right. We will later call these Dirichlet boundary conditions, but don't worry about that for now, okay? So that's a boundary value problem. So far, with the tools that we have, what we learned about ODEs, you might suggest, well, let's turn this into two first order ODEs, each with, because they're first order, they only require one condition, okay? And then treat them as two initial value problems. The challenge with that is that's a method called the shooting method. It's a very ancient method, but it is not the most general or most effective. So I will not teach that in this chapter. Instead, I will teach how we solve boundary value problems using finite difference methods, because they are more general, more robust, but each problem is gonna require its own specific derivation, okay? There's no like general one unique formula. Like we did with initial value problems, for the forward Euler method, UN plus 1 is UN plus delta T times right-hand side, right? That was generic enough, whatever the right-hand side is. Over here, it's gonna, the system of equations that you'll end up with, the solution procedure, is gonna depend on the problem at hand. So again, let's take the heated rod example, okay? Fixed temperatures are known. At the left, call this X equals 0, X equal L. So we have fixed temperatures, T left and T right. And this is our governing equation. Like I told you earlier, we're going to call this HP over lambda AC. Could just call it a capital H. It's just a coefficient. Has to do with the size of the rod and how the type of fluid you're using, whether air or water or oil, to cool or heat the rod. Okay. So now, based on what we did with initial value problems, what is the first step we should do here? Go, groups. You can look at your notes. First thing has to do with the domain. Okay, after that. Wait. That was hilarious, man. Thanks. Okay, after you print it out, what do you do? You are going to give us the answer. What do we do to the domain? Okay, remember in the initial value problems, we had to define, the points, right? So the first step is to actually discretize the domain. Just like we did with the time domain in initial value problems, we need to know, because we are discrete, we need to know at what points we are trying to find the temperature. And that is completely arbitrary. It's up to you. It's up to the user. Okay. So that's the first thing you want to do whenever you are dealing with discrete integration of ordinary differential equations, even partial differential equations. So the same thing we did with initial value problems, we're going to do here. We're going to discretize or split the domain into n equally spaced points. Okay. The spacing we're going to call delta x. And then we're going to assign an x value to each one of those points. We did this early on, remember, when we did linear solvers. So this is an array of grid points, okay, or abscisses along the rod, location on the rod. We do this with a length space. x1, x2, all the way to xm, okay? And you know the actual values of those, okay? Now, we assign a variable for the temperature value at each one of those points. So T1 on the left, you know it, it's T left. And then T2, T3, all the way to Tn minus 1. And Tn, the last point, is T right, which you know as well, okay? And our goal, our objective is to use the ODE to find T2, T3, all the way to Tn minus 1, okay? I know we did this before, but now we're going to understand what we did to obtain the matrices, the systems that we did with. So now the next question, this is the ODE d2t by dx squared ht minus t infinity. The next question is the governing equation valid at these discrete points? Yes, go ahead. I knew you were going to ask a question. That's why I pointed. No, the time, so steady state, typically in heat transfer problems, there's both a time derivative and a space derivative because things change in time and in space, okay? So at a given point, the temperature might be rising over time or, you know, decreasing, but there's also change from one point to point. So when you assume steady state, you knock out the time derivative, so you're left with an ODE, okay? So the question, is this equation valid? Yeah, Kimball is nodding. That's right. Absolutely. It's valid over the entire domain and specifically at those discrete points. That's very important. Remember when I discussed that in initial value problems, because that is going to allow us to apply the ODE evaluated at any one of those discrete points and then make an approximation. So yes, it is valid at each one of those discrete points. So at point 2, this is what it looks like. d2t by dx squared at point 2 is equal ht2 minus t infinity, right? You know, at point 3 and at point I, at an arbitrary point I. So now let me ask you this. Is it also valid at the boundary points? Yes, it is valid. But we don't need it because we know the temperature at the boundary points, okay? We know the temperature at the boundary points. We don't need to evaluate it at the boundary points. All right, so now I is in representative point, Ti, so it could be 2, 3, 4, n minus 1, whatever. That's a representative point. So that's a representative equation, okay? Now, again, based on what we did with initial value problems, what is the next step in trying to solve this numerically? So just describe to me, what do we do? So now we have, our objective is to find T2, T3, Tn minus 1, right? Or Ti, right? But over here, I have this thing, d2t by dx squared. I don't know what it is. Okay, so I need to untangle that and express it in terms of Ti, T2, T3, right? So what did we do with initial value problems, with the time-dependent problem? What was the step that we did here? Yes, we applied the finite difference formula to approximate what, Evan? The second derivative. That's right. So that's the step, is to approximate the second derivative, okay? So now go grab your notes, pick the right chapter in your notes and fill in the blanks here. I want you to approximate the second derivative. There was a formula that we used in our table of formulas in one of the chapters. You will find as a chemical engineer that approximating this second derivative is going to be with you for life. And you will find that eventually you'll remember that. Okay, it becomes ingrained. You remember that formula, okay? So the more you practice it, the more you see it, the more likely it will stick in your mind. Anyone got an answer? So go grab your finite differences chapter and get me the right derivative, second derivative, and evaluate it at point I. Rich? Correct. All right. This is the approximation of the second derivative at point I. It relates the values of the temperature at I minus 1, at I, and at I plus 1. Okay? It's sort of weighing the effect of the temperatures at the neighboring points, only at the very close points, okay? Only at the points close by to point I, okay? Over delta x squared. So now we can ditch this. Now we have a relation between the TIs, which is kind of what we're after, right? Our objective is to find formulas for TI, for I going from 2 to n minus 1, correct? Okay, so now this is our formula. I'm going to rearrange things a little bit. Like we always do, we put the unknowns on the left-hand side and what you know on the right-hand side. So I'm going to multiply by delta x squared and place the unknowns on the left-hand side and what we know on the right-hand side. So you get on the left-hand side, so you have delta x squared times HTI, right? So you get that number. And then you multiply by a negative sign. Oh, hold on. Do I have a typo here? Nope. It's the infinity minus, yep. So that's correct. Ti minus 1 minus 2 Ti minus H delta x squared Ti plus Ti plus 1. So you get this formula at an arbitrary point I. Okay. So this formula is valid also at each one of those points, right? So it's valid at point 2. It's valid at point 3, at point 4, all the way to point n minus 1, correct? So now I claim that we have all the ingredients to solve for the unknown quantities, T2, T3, all the way to Tn minus 1. So if you think that's if you agree with me, I'd like you to explain why and what to do next. And if you disagree with me, I also would like to explain why and what to do next. So I'm claiming that this one equation is actually a system of equations, right? When you apply it at T2, T3, T4. So go ahead, try. Apply it at T2, T3, T4. I'm claiming that this equation turns into a system of equations when you apply it at each one of those points on the rod. This is a representative equation for the temperature at each point on the rod, okay? So this is valid at 2, at 3, at 4, all the way to n minus 1. Nathan.
Well, how do you solve for T2? Let's make it put T2 for Ti plus 1, Ti minus 1.
Oh, on the left side, you know T1, right?
Yeah. But in the equation, you have the Ti minus 1. So like left of T1.
No, you don't apply at T1. Your objective is to find the temperature at each point, right? So the equation at point 1 is T1 equal T left. That's the equation at point 1. The equation at
for T2, then you need to have the T.
So write it down. You're still thinking in terms of a single equation. But who said it's a single equation? Right? So I know you know the answer. Okay, so Nicholas is saying, yeah, we get a diagonal system of equations. You're right. Okay, Evan.
I was going to say, could you just set your delta x to be half of that and then find
No.
okay.
No. Those are don't. It's the answer is simpler.
Okay.
Occam's razor. Are you familiar with the concept of Occam's razor? Yeah. So don't, the most likely explanation, the answer is the one that is just kind of straight in front of your eyes, right? The simplest explanation. So you don't have to, it's not a trick question. Just take this equation and write it down for each point. Think about unknowns and knowns, what you know. So write it down, 1, 2, 3 points, okay? Don't try to outsmart the equation, trying to say, oh, I'm going to extract T2 in terms of T3. Just write it down as it is. Write it down for point 2, point 3. You know at point 1, you know T1 equal T left. Go ahead and write it down. Start with T1 equal T left, and then go ahead, write the equation for T2, write the equation at T3. So at T2, you don't have T2, right? You have this full equation at point 2, right? You don't have T2 equal this, right? And so I, you should replace, when you're at point 2, you replace I with 2, right? Don't forget to replace I with the point at which you're at, okay? Don't attempt to solve for the temperature. Again, guys, think in terms of, don't think of a single algebraic equation. Think in terms, just write this formula at point 2, point 3, point 4. Write this formula, just write it down. Yes. No. So here's how you think about it. I is a representative point on all of these grid points. At 1, you have a special equation called T1 equal T left. That's a known quantity. So you start there. At point 2, I is equal to 2. So you get T1 minus something times T2 plus T3, right? And so on, okay? So we did something similar in the linear solvers chapter. Okay, you got it. So you continue that. Yep, there you go. You see it, right? Yeah, because it's not one equation, right? You got to put them all next to each other to see it's a system. Okay, okay. Now you see it? Are you satisfied now? Okay, so now you call it AX equal B, okay?
Yeah.
Yes.
But I was wondering if we're like figuring out every point from like the previous points.
You're not figuring out from the previous one. You have to solve them all together.
Is there any error that's like propagated throughout?
There is an error that has to do with the discretization. So that discretization, converting the second derivative to an approximation, introduces a second order error, order delta x squared, and that's the only error that is carried out.
We solve it all at the same
Right.
time.
You have to solve it at the same. You cannot march it. You can't, right? You have to solve it at the same time. Now, the system, like the Jacobi or Gauss-Seidel, is kind of a marching, right? It solves equation 1 for x1 equation, but but that's what matters, the system now. All right. So let's see. Okay. So T1 is T left. Okay. Yep. All right. So continue at point 3. Right. You got to write it down. Niall got it. Okay. But you don't recognize yet. Okay. Well, yeah, you're still thinking in terms of single equation and single unknown, but you don't. You have. So think. So here's a trick, Niall. So replace. Replace T1 and T2 and T3 by like X, Y, and Z, etc., and replace all of this with a coefficient. What do you get? You get AX plus BY plus TZ plus, It does. All right, you guys got it. Good job. Good job. Good effort. Okay. Anna, you got it? Okay. Okay, almost there. Perfect. Okay. Kara? Okay, do you see now the system? Okay. Okay. So we had mixed feedback. Okay. So this equation, we use it in on the chapter on linear solvers. And these slides that follow are just a copy paste of those that you saw in the first and the second chapter. Okay. So this is a system of linear equations. Okay. And to see that, you need to write that equation above, take it and apply it at each point. Many of you are still thinking in terms, oh, I want to solve for T2 in terms of T3 and T1, and then T3 in terms, don't think of it this way. Let the solution method do it for you eventually. But first, you need to see what the governing system is. And to see that, you need to take that discrete equation and apply it at every point. Now, at point 1, you know that T1 is T left. That's given to you. So we don't need that equation. We don't need that discrete equation, okay? Besides, like many of you notice, if you apply that equation at point 1, you're going to get a T0, which doesn't exist. Okay, so forget about that. We know the temperature at T1. Don't worry about it. Put T1 equal T left. Now at point 2, you simply substitute I with the value 2. So you get T1 minus 2 minus coefficient times T2 plus T3 equals something, okay? At point 3, you get the same thing. You get T2 and T3 and T4. So now you're starting to see, you know T1, but in the second equation, you have 2 more unknowns that are T2 and T3. So you need an equation for T2 and equation for T3, right? So you go for point 3, you get an equation, you get T2, but you introduce, and you get T3, but you introduce 1 more unknown. So you keep doing that until you reach the end, and you will have as many equations as there are unknowns. And when you look at this, you have n equations and n unknowns. That's a system of linear equations. They're all linear, right? Okay, so when you put it this way, okay, now you can just convert it into a system of equations. So if you don't see this, the first equation is T1 equal T left, right? So that's 1, all zeros, T1 equal T left. The second equation is T1 minus coefficient T2 plus T3 equal minus h delta x squared to infinity. And that continues all the way to the last point. Okay. We did this in January, but now you know how we obtained it. The only thing that we didn't know back in January or whatever month that was how we got this system of equations. And many of you were like, how did you get this? Explain to us. This is the explanation, right? Okay. Oh, okay. You can ask now.
So does this connectivity only work with fixed values on endpoints, I guess?
So we're going to talk about derivatives. So typically, I'll discuss this in a minute. Yeah. But that's why finite difference method depends on the problem. Okay. So if you remember, we kind of did this, right? When we built the linear solvers way early in the semester. And this was called a tridiagonal system of equations, right? So you could use the TDMA or you could use linear algebra.solve. It's okay. We're not going to worry about iterative solvers now. What we care about now is how we build this system. And so remember, we did this in January. I'm like, if I say one more time, remember, we did this in January, you're all going to leave the class. So, all right, let's go ahead and refresh your memory on this. Okay, if you forgot, you probably forgot how to do this. So let's do it again. There's a notebook called Boundary Value Problem Example, Heated Rod, okay, with gaps. Go ahead and grab that from the files or the Boundary Value Problems module. Okay, you guys still hear me on Zoom?
Yeah, Professor.
Okay, so my battery is blinking, so I'm gonna replace it right now while you all load up your notebooks.
Professor, we can't hear you on Zoom.
Can you hear me now?
Yes,
Yeah.
thank you.
Thank you for speaking up. I appreciate it. Okay. So yes, so lower diagonal, now main diagonal, and then you fix the first point and the last point, right? Just like it's seen in the diagonal. And then the upper diagonal. So I had a mistake here in lower diagonal. It should be np.1s of size n-1, correct? Thank you, Professor Saad, for correcting yourself. Okay, so the upper diagonal, same thing, right? np.1s of size n-1. And the last entry, the first entry in the upper diagonal, so UD0 is 0.0. So now we're not going to use any TDMA or iterative solvers because we're focused more on obtaining these matrices. So in chapter 2, I told you I will give you the system of equations. Okay, and then you focus on how you solve that system of equations. In this chapter, you are responsible for obtaining the system of equations, but use the simplest method to solve it. We're going to use just NumPy and algebra solve. Okay. So remember also that diag function. So for the lower, you can combine multiple vectors. So the lower diagonal, main diagonal, upper diagonal, and give them the order with respect to the main diagonal. The main diagonal is always located at 0 with this np.diag function. So we put the main diagonal at 0, the lower diagonal at -1, and the upper diagonal at +1. Okay. We need to build the right-hand side array. So the right-hand side also is it mostly contains minus t infinity times delta x squared times h. Okay. So we're going to create a NumPy array of size n, the same size as the number of points, right? Filled with t infinity dx squared times h, and then we'll fix the first and last points. All righty. So what we're going to do is minus t infinity times dx squared times h times np.1s of size n. And then we fix the left boundary, which is t left, and fix the right boundary, which is t right. So those were defined just up here, okay? T left and t right. And I guess the length space, you can do it from 0 to L. Okay, linear algebra does solve. You give it the coefficient matrix A and the right-hand side. Okay, and then you plot your solution versus X. Okay, and it crashes. Name NumPy not defined, of course. Okay, fix the endpoint. Object that does not support item assignment. Oh, NumPy.1s times np.1s of size n. Okay. Oh, geez. What the heck is going on today? Yes. Oh, you're right. You're right. Oh, thank you. Thank you. That was you, right? Thank you for having my back. You always got to have like a student and the, you know, or someone like one of your TAs. Okay, so now you can change the temperature, you know, like we did last time, but that becomes just, you know, a moot question, right? So you change T right, T left, change H. You know, if you make H really high, like 1,000, you know what happens then? The rod is going to immediately catch the temperature of the air. because the heat transfer from the air or whatever fluid is passing on that temperature to the rod very quickly. So you get that temperature very, very quickly, okay? However, if you make H very, very small, what you're going to get is essentially, so this should be a straight line. So PLT dot limit, it should be 300. Let's do 500 over here, 600. You get just a straight line. Okay. 1 or 10. Let's do 10. Okay. Now, what I have down here is a little trick for you to visualize the rod in a kind of a little nicer way. If you execute that, it assigns a color map on the rod, okay, with red being the highest value and blue being the lowest value, okay? It's a pretty cool little trick to just kind of illustrate how the temperature looks like, right? Because when you look at this contour plot, you're like, yeah, the highest temperature is at the right, the lowest temperature is at the left, indeed, because that's what we assigned here. T right was 600 and T left was 300. If you go to T right 300, then the bottom figure is going to swap. You're going to have the lowest temperatures on both ends and the highest temperature in the middle, okay? Right? All good? Any assistance needed with the code? No? Yep. Perfect. Excellent. Okay. Shall we return to the slides? Any questions on Zoom? No questions. Perfect. Okay. So we just did this exercise. Now, going back to what your colleague just said, it's like, does this work only for problems? Yeah. One moment. You guys need help? Oh, okay. Yeah. Okay, perfect. Hey, I spend hours on picking a font, you know. All right, try the Viridis is the one of the best ones, but you know, or red, yellow, blue, inverted. Anyway, so Ethan, I'm going to talk about boundary conditions now. Okay, so your colleague said that, well, does this only work when you fix the temperatures at both ends? Well, what we did, yes, it works only for what we do when we fix the temperature, but could you have other options at the boundaries? You know, rather than fixing the temperature, could you do something else? Yeah. Turns out there's two general types of boundary conditions that you apply on differential equations. The first is called a Dirichlet type boundary condition, where you specify the value of the dependent variable at the boundary. Like here we specified the temperature, okay, or you specify the pressure, or you specify the concentration, you know it. But there are other types of problems where you don't know the actual temperature, but instead, or you don't know the actual value of the dependent variable of the quantity, but instead you know the rate at which this quantity is being fed into the system or extracted from the system. So for example, you could know the heating rate, okay? It's changing, the temperature also changes if the rate is changing. So you don't have a fixed temperature, rather you have a fixed rate of change at the boundary. Same thing with concentration, or you could have a flow rate, for example. So that type of boundary condition is called a Newman boundary condition, where instead of specifying the value of the dependent variable itself, you specify the value of the rate of change or the derivative of the variable at the boundary. So rather than putting phi0 equal t left, t0 equal t left, and t right, tn equal t right, you do dt by dx is equal beta left, and then dt by dx at n is equal beta right. Okay, this is still a fixed value. Now you could even complicate it, but you know, we're not going to go in that direction. But you can make this also a function of the temperature, for example. But you know, that becomes a secondary issue. But what matters here is that now you have a derivative. specified at the boundary. Now that complicates things quite a bit. Okay, so let's see how it complicates things. So that equation, the governing ODE, is still valid. It's steady state heat transfer in a rod. Whether you have fixed temperatures or fixed Newman conditions or a mix of both, doesn't matter. That equation is valid. So in this case, then I'm going to illustrate here. I'm going to fix the temperature on the left. So it's a Dirichlet boundary condition on the left. But on the right, I'm going to put a Newman boundary condition. dTn by dx at the right point is equal to beta. You know beta. Okay, you know the value of beta that is user specified. Okay. So our previously discretized equation is also valid. That's what's nice about this, is that once you discretize the equation, it's the same for all different boundary conditions, but you have to derive the system of equations differently for different boundary conditions, okay? So there's no one generic formula for all of them. You have to derive it for each configuration. So this is still valid at all the points, okay? Except that we need to do something different at x equal L. So at x equals 0, we know the temperature, so there's no need for an equation for the temperature. But at the right point, you don't know the temperature, you know its rate of change. So we need to do something different, okay? So what we do, we take the governing equation and also apply it at the boundary point. Okay, so that's the trick here, is we actually take the full governing equation and apply it at the boundary point. That boundary point is n. So you replace I with n, you get Tn minus 1 minus coefficient times Tn plus Tn plus 1. But you say, Dr. Saad, there's no Tn plus 1. Does not compute. Okay? Error, 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 error. That's correct. But we are going to imagine a ghost. Okay? Ooh, the ghost of Tn plus 1. Sorry. I do a lot of dramatization with my son, so this is part of it. So imagine there's a ghost temperature. It doesn't exist. Okay, suppose that it's just there, just to allow us to play around with the algebra so that it's no longer there anymore. So we're just going to assume that there's a point out there. We're not going to say anything about it. It's just Tn plus 1. It's a placeholder for over here. Okay. Now, there's one piece of information that we have not used yet. Like I said, we need to eliminate this Tn plus 1. There's one piece of information we have not used, and that is what? The boundary condition at n, the Newman boundary condition. So if you take dt by dx at n, you know the value of dt by dx is given to you as beta. And if you use finite difference on that boundary condition as well, then you can relate Tn plus 1 to another point in the domain. So essentially eliminating Tn plus 1 altogether. So if you take a centered difference for dt by dx, and now I'll ask you why I chose a centered difference. If you go back to your finite difference chapter, the formula for the centered difference for the first derivative at point n is Tn plus 1 minus Tn minus 1 over 2 delta x. And that is given to us equal to beta. So now you can express the unknown point, the ghost point, Tn plus 1, in terms of known quantities or quantities that we are solving for. So you eliminate that point altogether, right? You see how powerful that is? So that ghost point was only a mathematical trickery to allow us to just kind of carry out the algebra, and then we're not going to need it anymore. At all, we're not going to need it. Okay? So that gives you the point Tn plus 1 in terms of beta delta x, which you know, and in terms of Tn minus 1. Now, Tn minus 1, you're solving for it, but it has an equation. It's part of the system. Okay? So we have an equation for that. We're not going to worry about it. It doesn't add any more degrees of freedom, per se. So now, when you take Tn plus 1 and substitute it in that last equation, this is what you get. You rearrange term, So it only, you rearrange terms and you get this. Okay. So now what happens for this case, when you have a Dirichlet condition on the left, you have T1 equal T left. For all other points, you have this equation. Okay. So T1 minus 2 minus coefficient times T2 plus T3 and so on, all the way to the last point where you also have a different equation. You're going to have a different equation. And that is 2Tn minus 1 minus coefficient times Tn equal whatever this is. So over here, there's a typo. This should be Ti. Okay. Let's fix that. Actually, over here. This is it. Okay. Oh, no, not over here. Apologize for that. Let me fix it. Give me a moment. So Ti. Okay. So for all the points in between, you get that full discrete equation. At the last point, point n, your equation is different, but there's no Tn plus 1 anymore. Okay? There's no Tn plus 1 anymore. So for 5 points, for example, for 5 points, you get the same kind of tridiagonal structure, except for the last point. So previously, we had 1s everywhere and a 0 over here, remember? Now we have a 2. Well, that's kind of what the math told us, right? And this one is still the same, but the right-hand side also changed. So that's kind of for 5 points, okay? Let's see what we have next. Okay, so now before we go and solve this in Python, why did I choose a second order difference for the first derivative? I could, Nicholas. Yes, thank you. Okay. So the reason I chose to approximate the Newman condition with a second order approximation, order delta x squared, is because everything we've done so far for the governing equation is order delta x squared. So if we go ahead and if we had approximated that Newman condition with a first order approximation like Tn plus 1 minus Tn over delta x, it would have introduced an order delta x error, a first order error, which will contaminate your solution entirely. Okay? Because the dominant error is always the lowest order error in your problem. So that's why we chose to use a second order approximation. Okay? So now go ahead, pull up your notebooks, copy and paste what we just did for the Dirichlet problem, but now hack in this system of equations for a mixed Dirichlet and Newman condition. Okay. Let me see if I actually, yep. Just go and do this. So copy paste the cell that we just worked on with Dirichlet conditions. Now you have to change the coefficient matrix just a little bit, right? Only the lower diagonal changed and the last point in the right-hand side changed. Maxime, 1 second. Yes, yes. So beta, beta, that's a number that is user specified. Once you get this programmed, just put a value for beta and see what you get. It's a heating rate in this case. Okay. For what? By what? Why? No, because when it's easier sometimes to measure the heat flux, right, than the temperature itself. So on your stovetop, for example, you initially when you turn it on, right, there's especially if it's electric, there's a fixed flux, right? But the temperature of the top is changing. right? It keeps changing, but the heat flux is constant. So you can measure that. Definitely, you can measure that. Oh, you got it? You got it? Okay. So now put beta equals 0. And hypothesize what happens if you set beta equal to 0. What should you expect to see in the curve? Okay, so you have an issue then. That's okay. Beta equals 0 has a special meaning. Think about that. Beta is the dt by dx, right? So it's the slope. There you go. Did you set beta equals 0? Mm-hmm. Yeah. So what do you get? 0 slope, right? So set beta equal 10 or 100 or something. Yep. Right? Okay. If you think you have a solution now, think about what beta means. Beta is the slope of the temperature at the right-hand side. If beta equals 0, your temperature curve should just flatten out. If beta is negative, your temperature curve should go down on the right. If beta is positive, your temperature curve should go up on the right. Okay? Should be slope upward, slope downward, slope 0. Okay? It's one of the best verification, visually verifying that you got a rational solution. Yes, beta equals, yeah, isn't that right? So now put beta negative, you should see it slope down, right? Like minus 100, for example, or 1 million, right? Yeah. It's going down because you're extracting heat, right? Now, the slope is one thing, the value of the temperature itself is another, right? So when you're extracting heat from that side, then your temperature is probably going to be dropping compared to the other side. Let me see, -2 beta, delta x not changing. Okay.
Change beta.
So did you fix your, yeah, you got to fix the, the lower diagonal. Did you fix the lower diagonal? Oh, you got it, d-1. Okay, so scroll up. Did you define beta as 100? Yeah, something is off. Nope, it's not changing. So are you -8 delta x squared infinity -2 beta delta x? And RHS. Yeah, this should be okay. So upper diagonal is here is ones everywhere except the first entry, and then diagonal. So h delta p that once. Okay, this should be correct. That's weird. X. Okay. So restart your kernel, please. So yeah, just run kind of the first cell and the last one. And because this should be okay. Did you run this one? Yeah, this is weird. It's not even right. So is this your local host? Let's see, if you don't mind. Print it out. Right? See what's going on. Yeah, that's kind of so weird. So right hand side, A is lower diagonal, P dot ones, LD. Lower diagonal is okay, up 2, and dx lower diagonal 1, 2, and then 1. Okay, the last entry here is wrong. d-1 is wrong, right? It's -2, so you don't change it. Okay. I think you have a problem with the main diagonal. Yep, there you go. Yeah, you had the same problem over there. Yeah. Okay. Pardon me. There's no T right anymore. Oh. Correct. So you're setting the last value of the right-hand side. That's what RHS minus 1 is giving you, correct? And that is, what is it? Minus h delta x squared t infinity minus 2 beta delta x. Correct? Yeah. So that's what you need to put in for the last point, for the last right-hand side value, right? It's a system of equations. You're just telling it the right-hand side of that last equation, right? Yeah. Kimball, you got it? Yeah, yeah. So as you change this, perfect, great. How's it going here? Okay. Okay. Well, if you need help, let me know. Kara, you got it? If you put beta equals 0, what do you get? Just a flat curve up at the right. So there's an issue. So your main diagonal is wrong. The last entry on the main. Don't forget the last entry on the main diagonal. Okay. So, right, it's minus 2h. Yeah. Nathan, did you want something? Yeah, last entry of the diagonal. Nope. Look at the main diagonal. The last entry is minus 2h delta x squared. H plus delta x squared. Yep. So
Beta is negative 100.
That's right. So if you put beta equals 0. Perfect, right? So the curve, the slope is 0, right? And then if you put beta positive, then you should go up. Perfect. Okay, you guys got it? Okay, any help here? Yes.
I is not changing limit.
Yes.
Beta.
So I think you have a problem in D. So D minus 1. Well, nope, you got it. That's correct. So D0 is 1, and then minus 2. Delta minus 2 plus h delta x squared, correct? Lower diagonal. So your lower diagonal is off. You needed 2. And this one is the other way around. You got them the other way around. You put a Dirichlet on the left-hand side, a Newman on the left-hand side. But that's fine. You know, that's another problem, though. Yeah. Still off.
Still off.
Yeah. So the upper diagonal is the other way around. The first entry on the upper diagonal is 0. So UD0 is 0. Yep. And the other one, D minus 1 is 2. No, sorry. Don't change that one. My bad. Yes, this one. D lower diagonal minus 1 is 2. That's correct. So yep. So just minus 1 is 2. So run it. There you go. Now put beta equals 0. The slope should be 0. You guys got it?
Mine's looking like this with the beta. Here's, I'll show you the beta 0.
Yep.
So,
Yeah.
Oh, is that right?
Yeah. Oh, sorry. Yeah. Yeah. Why not, Ethan?
I don't know.
Even,
Just
yeah. No.
I just
Beta
have to
equals 0. Slope is 0.
Oh, yeah,
Right?
It's like
Yeah.
this.
Slope negative. Slope positive. Right? That's kind of the quickest check.
Okay,
Ethan, you got it.
I think so.
What is this beta?
This is beta equals 1.
So okay.
Infinity is like room temperature.
Yeah. Perfect. Now put beta equals 0. Yep. So slope is 0. Right?
Thank you.
Okay. Let's see. Need my help?
Oh,
Yep. So your D is off. Just comment this line out, right? Because that's the last equation, right? It's in the previous problem, it was 1, correct? In this problem, it's still minus 2 h delta plus h delta x squared, right? So that's this last entry here. This last entry right here. Okay.
So like you can solve
You can, yep.
what exactly is that?
It just means that's kind of the heating rate that will get you that temperature like you had the last problem. Yeah.
Is there a difference in the heating rate?
Sometimes it might be easier to measure that because you can get that from directly from, for heat, for example, from current, which is rate of, electron flow, right? So you can relate that to the heating element, right? And you don't know exactly what temperature you're going to be getting, right? So. Okay. Looks like most of you got it. All of you got it. Okay. Okay, so it's telling you that d minus 1, so is d minus 1, you're putting, this is one entry, right? D minus at -1, but you're putting an array in d minus 1, which is wrong, right? So this is a single value. D minus 1 is the last entry in the array of d.
Yeah.
D itself is an array, but d minus 1 is just in value. So you should just comment this entire line, right? Because when you created d equal -2 plus delta x squared h, you created all of those entries, right? Including the last point. But you're only changing the first point to 1, and that's it. So you comment that out, okay? Okay, so now same thing with the right-hand side. You have the same issue with the right-hand side. So the right-hand side, you got to adjust it because the last entry at the right-hand side is also just a value, right?
So where
It's correct, but the mistake is mp.1s. That's your mistake, right? So why are you creating an array where you're supposed to just put a value, right? Just a single value. Does that make sense?
Yeah.
Yeah, when you created this, thing over here, it created an array of endpoints, RHS at 0, RHS at 1, RHS at 2. Each one of them had a single value, okay? So when you change RHS as 0 to T left, you're picking the first point. You change the last point, you don't need an array. You just need to right? So, yep.
Does that still mean?
There you go. Now this is beta equals 0. So you see that the slope is 0, right? Okay. Okay. So let's see. Okay. So for the sake of those who are on Zoom, okay, I'm going to go ahead and copy this, put it over here. Okay. So everything is the same. Okay, everything is the same except for a couple of things. So the first one is, let me get the slides. Let me get the slides here. Window. Okay. So if you look at the slides, sorry, I don't know where my slides went. Okay. So if you look at the slides, the thing that changed with the previous problem is this last entry on the main diagonal. Okay. In the previous problem, this was 1. Now it's the same as all the other entries in the main diagonal. In the previous problem, this was 0. Now it's 2. And in the previous problem, this right-hand side was only -h delta x squared t infinity. Now we need to subtract from it -2 beta delta x. So those are the 3 things that I need to change. For the lower diagonal, the last entry is 2. For the main diagonal, I don't need to do anything at the last entry. We already created -2 plus delta x squared h. The upper diagonal doesn't get affected. Nothing here changes, except for this last point for the right-hand side at -1. It is equal to -t infinity, etc., -2 times beta times delta x, correct? So we had it -2 beta delta x. And let me go ahead and define beta over here. And I put it at 1. Okay. Oh, yes, I did the, yep. So correct. Thank you. Okay. So that's beta equal 1. How do you check that this makes sense? You do 3 tests. For beta equals 0, you're saying that the slope of the temperature dt by dx at that point is 0. So the temperature curve is going to go flat at the right-hand side. Okay, so beta equals 0 is going to give us, look at that, a flat curve over here, right? Almost flat. No matter what you do to T infinity and the other temperatures. So we don't have a T right anymore. Now let's do T infinity at 200. Okay, look at that. It's going to go flat. Okay, even if you change H, if you put H 1,000, it's going to go flat. If you put H 0.1, it's going to go flat. Okay, doesn't matter. All right, 500 T infinity, same thing. 1,000. Same thing. Another test for beta positive, the curve should have a positive slope. For beta negative, the curve should have negative slope. Okay, so for beta positive, let's do 100. It is indeed a positive slope. For minus 100, it is a negative slope. Okay, it's wild because you're not fixing the temperature, you're fixing the rate of change. It changes the entire, because you don't know what the temperature is at that point. All you know is the flux. And it's going to pick whatever temperature it wants to pick to get to have that flux, to get to have that slope over there. Okay? Now you can do this for the left point, for the right point, for both Newman conditions. Okay? But you have to derive it every time. Okay? And that is something you need to master. Okay? You need to know how to do very well. Okay, apply the discrete equation at the Newman boundary. So those are the steps. Are kind of, you can list them. Apply the discrete equation at the Newman boundary. Imagine a ghost point. Okay, eliminate that ghost point by discretizing the Newman condition. Okay, so you discretize the Newman condition. You extract the value for Tn plus 1. You plug it in the governing equation, and you're good to go. Okay. We have time to do an example, and then I will let you go. Okay, so I'll go through this example kind of briefly. So your governing equation here is d2u by dx squared equal x squared u. It shouldn't scare you. It's a second order ordinary differential equation. It has two boundary conditions. Du by dx equal alpha on the left-hand side, and u at the right-hand side is equal to beta. It's a boundary value problem. Okay, it has a Newman condition on the left and a Dirichlet condition on the right. Go ahead and discretize. This is a classic problem that you will get. This is a classic problem that you will get in the exam. Write the discretized equation at an interior point I. Forget the boundaries now. Any point in the middle. What is the discrete equation? Open your notes. Look at what we did in the previous slide. Okay. You know x1, x2, x3, and xi. You know those. Okay. That's right. Forget about the endpoints. The interior equation is just kind of do the discretization on the left-hand side, on the right-hand side, whatever that is, x squared I ui, right? Just apply that equation at an interior point. It's a different equation. Yeah, but use the second derivative formula from your previous slides, okay? Which is ui plus 1 minus 2ui plus ui minus, or ui minus 1 minus 2ui plus ui plus 1 over delta x squared. Okay, all right. You got a Newman on the left boundary. Expect questions like this on the final exam, okay? So you need to master these examples. It's very correct. More than correct. Could there be something more than correct? Okay, so make sure you put the indices here, right? Yeah. Yeah. Perfect. Perfect. Okay. So what is X here and what is U? Remember, this is discrete values, right? At what X is this and what U? The discretized equation is simply the tautologically, it's the discrete form of the equation. So it's essentially the approximation to the equation at discrete points.
Okay, so
Yeah, that's it.
No.
No, just at an interior point. So write the formula at a generic point I going from 2 to n minus 1, okay? X squared, think so, yes, good job. Yep. Okay, and multiply out by delta X squared and just give me a the generic formula for the discrete equation at all interior points. You're doing the boundaries. Doing the boundaries too. Yeah, so it might help if you, so don't forget indexing over here. So the first step is you really need to simplify this equation as best you can so that it looks very clean. And then you apply that at the Newman boundary. And imagine there's a imaginary point, and then discretize the Newman boundary condition. Michael, you working on it or?
Yeah.
Okay. Okay, anyone needing my help? Okay. So maybe I'll write it on the boards. Sorry for those on Zoom. I'll show you the slides in a second. So what I would do is I would take this equation, d2u by dx squared is equal to x squared u. First, I apply it at an arbitrary point I. So you get xi d2u by dx squared at I equal x squared I times ui. Then I substitute the second derivative with its approximation at a point I interior. So that's ui minus 1 minus 2ui plus ui plus 1 over delta x squared equal xi squared times ui. Now I simplify, I multiply by delta x squared on both sides. So you get a delta x squared times xi squared times ui. And you have ui and ui, you combine them together. So you get your discrete equation ui minus 1 minus 2 plus delta x squared times xi squared ui plus ui plus 1 equals 0. Okay. Is that what you got, Maxime? Yep. So at an interior point I, okay, This is what I would get. Don't forget the indexing for the right-hand side. So again, the simplest thing you do is just take that equation and apply it at a point I. Just take it and put I everywhere. Then discretize, approximate the second derivative. This is what you get. So now at the left boundary, where we have a Newman condition, I equal 1, write the discretized equation. Just write this equation at the Newman boundary. And assume there's a ghost point. So essentially put I equal 1 in that discrete formula. There's nothing deep about this, just I equal 1 in this case. Put I equal 1 and let the equation give you whatever it wants to give you. So take this equation before you discretize the boundary condition itself. Take this equation and apply it at I equal 1. So replace I by the value 1, right? So you're going to get a U0. And that is our ghost point. Okay, we got 2 minutes left. Just apply the discrete equation, this discrete equation at point I equal 1. Simply replace I by 1 by the value 1. Now, because we know there's a Dirichlet, there's a Newman condition there, that's why we applied the equation over there. So that is going to give us a ghost point U0. We don't know what U0 is. I'm going to say it's imaginary, it's temporary. Excuse me, until we figure out how we get rid of it. Now, the next step is to eliminate U0 by discretizing the Newman condition, du by dx equal alpha at that point. And I'll give you that formula. So du by dx to second order is u2 minus u0 over 2 delta x. Notice how I highlighted in red. Equal alpha. So you know alpha, you already have u2 in your system of equations, then you can eliminate u0. So you get u0, you express it in terms of the variables that you're solving for. That's what you're doing here. And you simply take u0 and put it in here. Okay? Zip it, lock it, and put it where it belongs. Okay? u2 minus 2 alpha delta x. I just took this value and put it up here. Okay. Now you get that equation. You get an equation for relating u1 and u2 at that first point. Okay. So the way you can think of it is that you now have a linear equation, one equation at every point. Okay. You move everything you know to the right-hand side, which is 2 alpha delta x over here. Now you have that equation at point 1. At the right boundary, it's a Dirichlet condition. You know un. There's nothing you need to do. Un is beta. You don't apply the discrete equation at that point. Although it's valid, you don't apply it there. You don't need it. And that's your system of equations. At the first point, you have this equation. At the last point, you have un equal beta. And everywhere in between, you have this equation up there. Okay? And then you simply turn this into a system of equations. At the first point, you have that first equation, minus 2 plus delta x squared x1 squared. Don't forget the xi, times u1 plus 2u2 equal 2 alpha delta x. You have zeros everywhere, and you have that full tridiagonal structure. And then finally, at the last point, you have un equal beta. There is no general formula for boundary value problems. I can add a first derivative to this. There's an infinite number of variations. But if you follow this strategy, discretize the equation, discretize each term, separate the unknowns from the knowns, Do it at the interior points. If you have a Dirichlet, you know the value. If you have a Newman, you have to apply the discrete equation. Imagine a ghost point, and then eliminate that by approximating the Newman condition. Okay? I'll see you on Thursday. We'll make this even harder. Okay? Thank you. All right. Zoomers, do you have any question?
I think I'm the only one left. I think we're all good.
Oh, hey, Alicia. Sorry, yeah, I just saw you. Well, thank you.
Thank you.
Bye.
Bye.